So now what I want to do here is that I want to go in and look at one more example, but I want to start off by talking about the second class of collisions, which are called inelastic collisions. So we have to kind of review a little bit to make sure that you're with me. What I said last time is that there are two categories of collisions. We said that there were elastic and inelastic. Inelastic is more complicated. And what you're going to find here is that typically inelastic is broken into two further, not farther, but further categories. And it turns out that this one is typically the hardest one, believe it or not. So we have what we call inelastic, but in the inelastic, it turns out that there's two kinds of inelastic. Believe it or not, one of them is called inelastic collisions. And the second one, which is easier, is called completely inelastic collision. This one is the most challenging. This one is probably the easiest. So let's sort of like review before we get started here. So let's go back. What do I mean by an elastic collision? What do I mean by that physically? What we said here is that this is a perfect collision that creates no sound, heat, or light. So in the way we deal with elastic collisions here is that we drop a ball. And as we drop a ball, it goes downwards. And then right before it hits the ground, remember, we have to worry about this. There's a process of deformation that goes on. And what we pay attention to is what is the momentum right before the collision. And then we look at what is the momentum right after the collision. That's what we care the most about. What's happening before and what's happening afterwards. Only during the collision do we care. However, to get a sense if this is an elastic collision, what we find here is that the ball bounces up to the same height. So in elastic collision, as a dropped ball ball collide and return to its initial height. And what that really tells us here is that there is no loss in energy to, let's say, sound, heat, light. All of the energy stays in its motion. All of the energy stays in its motion. And I don't like using the word energy, but there's no way around it. So what's an inelastic collision? So an inelastic collision, this is not a perfect collision. And can create sound, heat, and even light. So when you drop them, so if I was to come back here, so if I was to drop them, the big difference in this situation here is that the ball, the momentums still work out just fine. Momentum is still conserved, which implies here is that the momentum of the system before equals the momentum of the system afterwards. And you know what? I did not say that up here. Okay, I should have said that. Ooh. However, energy, because some energy goes to sound, what we find here is that energy of motion is not conserved. And so what that implies here is that in this case, the ball does not return to its initial height. And that's the only thing we can say about inelastic. It's hard to identify. Okay. These types of collisions, let me be careful, of inelastic are the hardest to identify, and a calculation must be done to check if it truly is inelastic. You can't eye it and just say that. So what do? we deal with the easiest case in most of the time. So the easiest inelastic collision is completely inelastic. And what you find here is that you have two objects that stick together after the collision. And one example that we can look at here is that we can look at shooting a bullet into a block of wood. So what actually happens here? Well, you could imagine that I have a bullet and it's coming in with some initial momentum. And I'll call the bullet 1. So 1 in this case is the bullet. And then what I have here is that I have a block. And in this case, let's say that this block is at rest. And so this here too will then be the block of wood. So then before and after the collision, what happens here is that the bullet now embeds itself into the block. And as it embeds itself into the block, we know here that this now moves off with some final momentum that includes the mass of the bullet plus the mass of the block, but it has some final speed going to the right. In this situation, momentum is conserved. And the question is why? Because look at the system. When you look at the system, it's conserved because the collision forces are internal. Therefore, the total momentum of the system is still a constant. Energy is not conserved. And the reason why is that there is heating in making a hole into the block. So some of the energy has to go in and deform the block in order to make a hole for that thing to occur. So now let's go look at this next example here. So again, I'm going to modify 6.4 from what you actually see in the example sheet question, but it's still the same question. I'm just asking more details. That's all I'm doing. So here we go. So the question that we want to look at here, it says here that we have a 300-gram bird flying along at 6 meters a second. and it sees a 10-gram insect heading straight toward it with the speed of 30 meters a second. The bird opens its mouth wide and enjoys a nice lunch. What can you physically tell me about that? What do you expect of the bird? What do you expect will happen to the bird's motion? After the collision. Well, pictures. Boy, we got to think about a picture. I got to draw a bird. Ooh, I'm not really. Let's see. How's my bird going to come out? Well, I see the bird and it's coming. And what's it have? It has its beak wide open. Okay. So I could imagine that here's my bird. Ah, that's not so hot, is it? Drawing animals like this is not my forte. Maybe we should have it kind of come up a little bit pointed here, and it's in the state of motion, so maybe it has its wings out here flying, something like this. And if you're making fun of my picture, maybe you can show me your picture so that I could laugh at it as well. And of course, this is a yellow bird, right? It's a yellow bird. And what we're seeing here is that this bird, I'm going to call number 1. And what I know here is that this bird is now moving at some speed, which I'm going to call P1 initial. Now, what I need here is that I need a bug. So you could imagine here drawing my red bug. Maybe my red bug is moving through the air, something like this, and it also has a momentum of P2 initial going in that direction. So this is my before. So when I look at my system, I could see that the only external forces that could change momentum have to be horizontal ones. So if it's right before the collision, I shouldn't have an issue with this. So then after the collision, what do we expect the bird to do? Do we expect the bird to stop? I'm guessing that the answer is no. I don't expect the bird to stop. So what has happened now? So if I paste this thing and just modify this a little bit, the bird continues to move forward. I would guess that the bird is moving forward. But the big difference now is that the bug is now inside the bird. And of course, we got to be careful here because the bird doesn't need to have its beak open anymore. So we're assuming here that the beak here of the bird is now a happy bird. But I would expect that the momentum of the bird and the bug still move, let's say, in some other direction here. Let's say that it now moves at some P final in that direction. This is what I would expect it to be afterwards. So if I look at this thing, what does my momentum bar diagram actually say about this? Well, I got to pick my direction. So I'm going to say that this is my positive direction is to the right. My negative direction is to the left. So a momentum bar diagram tells me that I would expect that a big share of the momentum stays with the bird. And this bird is moving in this direction, to the right. The bug, on the other hand, even though it's moving relatively fast, it has a tiny mass. And because it has a tiny mass, I would expect that its momentum will be in this direction, the negative direction. So what happens afterwards? Well, there's a total decrease in momentum. I can see here is that now this is the total momentum of the system, because when I add them, it has to be the exact same quantity. So then afterwards, I drew these wrong colors. Let me try this again, just to keep color coordinated. I'm seeing here is that this guy should be in red. And then afterwards, this should be in blue, where most of the momentum continues to move in the forward direction here. So this is my mathematical equation. So my mathematical equation reads like what? Well, it says here from my picture here, it should be P1 initial minus P2 initial has to equal P final, which is then now a combination of masses that now move at the same final speed. So then the question, what's the final speed of the bird bug system? In other words, what is VF equal to? While using conservation of momentum, we can then say here that PF, which is M1 plus M2, VF, that has to equal P1, which will be M1 V1 initial minus M2 V2 initial. I could then solve for VF, and if I isolate VF, then you could see here is that I have this combination where I'm dividing by the two masses. So then if I look at my numbers then say that my bird here is 300 grams or 0.3 kilograms. It has an initial speed of 6 meters per second going to the right. Now, if I look at my bug is only 10 grams, which is a factor of 30, and that's 0.01 kilograms. And its initial speed is 30 meters per second. So if I plug in my numbers here, I then get a relationship that reads 0.3 kilograms times 6 meters per second minus 0.01 kilograms times 30 meters a second divided by the sum of these two masses. And so when we compute this, we get 4.80 meters per second for the final speed of the bird plus the bug. Clearly, the bug changed the speed of the bird. So then I have a question here. Why did the bird continue to move to the right after the collision? What if I asked you that and I said, quantify that for me? It has to do with the momentum. The bird's rightward momentum was larger than the bug's leftward momentum. In other words, if I calculate the momentum P1 initial, which is M1 V1 initial, and I'm just going to put in numbers here, I get 1.82 Newton second. If I calculate the bug's, and I just look at its magnitude, note that this is 0.3 newtons per second. So this tells me that because the bird's momentum was greater, which is equal to 1.8 newtons second, was greater than that of the bug, .3 Newton seconds, the system continues moving to the right. And nowhere does this say better than this diagram. So if I take that diagram, that's exactly what that diagram is telling me. I have a bigger momentum going to the right, so therefore the momentum has to continue going to the right. Okay, I'm going to stop here, and I'll say here that I will post these up here shortly. I set the homework for Monday, and we'll have a quiz on Monday. I'm expecting to grade the stuff this weekend. You know, how do I say this here?